Okay, so hello everyone, welcome. Um, to those who have attended any of these sessions previously, welcome back. I think everyone, at least who's here in person and on Zoom, has been to at least one of the sessions before. So good to see you all again. And today is our fourth out of what will be 5 sessions on the Machine Learning Primer Workshop. And the topics I'll be covering today are spatial data and convolutional neural networks, as well as autoencoders and latent spaces. There we go. Okay. So as I usually do at the beginning of these sessions, I like to go over the topics that we covered in the previous sessions and highlight what might be relevant. So once again, as I've pointed out before in our first session, we talked about traditional data analysis methods and in particular focused on data decomposition, dimension reduction. We then did an general introduction to machine learning ideas, particularly considering data types and input data labels. And then looked at loss functions and how we evaluate models. And then for the second session, we did more of an overall survey of the types of models that might be used in order to perform machine learning, and particularly the classical, more classical variety, before going on to what is much of the focus of many of these sessions afterwards, which is neural networks, their structure, and their training. So of these topics, the ones that will be relevant or will probably touch on to some extent today are going to be looking at data types and input data labels, as we talked about, or as I mentioned in the title of this, we're going to be looking at image or spatial data. We'll be looking at neural network structure for particularly convolutional neural networks, as well as the structure of autoencoders. And then also revisiting this idea of data decomposition and dimension reduction as it relates to doing this in a data-driven way using autoencoders. There was also a third session, by the way, since that was on recurrent neural networks, that's sort of tangential to what we're working on today. So I didn't include that here. So our outline for what we'll be covering, as I've mentioned, we'll be looking at spatial data / image data in convolutional neural networks, maybe looking at some of the requirements and some of the different problem types that we might encounter that are related to image data that are sort of unique to those. We'll then be looking at, I'll give you an introduction to what convolutional neural networks are and try and help you to understand what the filters are, is what we call, is typically the terminology we use for convolutional neural networks, and then take a look at some of the representational layers and how representations evolve over the evolution through a convolutional neural network. The second half is going to be about a completely different type of network called an autoencoder, which also has a feature or sort of a property to them called latent spaces, which I'll be sort of giving you an idea of how those work here. We'll go into the setup, the structure. We'll dive into some of the properties of the latent spaces and compare that to our low dimensional or dimensionality reduction techniques that the classical versions of those. And then I'll end with just a very brief introduction to a different type of autoencoder called a variational autoencoder, which uses some more of a statistical or probabilistic approach to performing that task. So starting off here, we have our spatial and image data. Okay. So for our spatial and image data, I'm getting, this is obviously something that's very familiar to everyone, but I just want to go into sort of the structure and what differentiates image data from sort of your standard, more like vector data. So what really makes image data is that it's defined on some grid with a finite number of points at specified locations. Each of those locations typically has equal size, and then we represent values at each of these locations or pixels using some intensity or some individual value, which tells us how strong or effectively what the intensity is at that point. And then that point will have a single value which contains a uniform shading or a uniform brightness. Of course, we only care about a single intensity or brightness when we're looking at, say, a grayscale image, as is shown on this slide. But if we move on then to, here we are. So if we move on uh, to data that, or images that have color to them, then we introduce some additional complications because we'll have 3 layers here, really 3 different intensities that we're measuring at the same time. It's not just the pure brightness, but we're looking at the red, the green, and the blue, which is where we get the term RGB data or RGB channels. And then an individual pixel is then going to be the combination or the superposition of these 3 color channels to give you that output. So that's sort of the structure of what an image is. I'm sure that's familiar to most people, but I just wanted to outline that as we move on to look at the following terms here. I want to outline a little bit because I think, especially with image data sets, there's one of the most important aspects to it is how labor intensive it is to actually label data. And this is true for a lot of the other data sets as well, but image data in particular has posed sort of a major challenge. And so many of the advancements in the methods that I'll be talking about today, and really it aligns with a lot of the advancements in general neural network, the popularity of neural networks, arose as a result of the publication of some large scale image data sets that were annotated and labeled. So I'll go into some of these data sets that came out in the latter half of the 2010s, which have some interesting properties and can be helpful if you just kind of want to play around with CNNs. So first one I'll talk about here, there's one that I'm not, or there's several, of course, that I'm not including. The first sort of like very famous broad image data set is called CIFAR, CIFAR 10, which is kind of a smaller scale data set, but is a very useful one to start on as a benchmark for a lot of like computer vision tasks. But I wanted to go into some other ones that you maybe haven't heard of or that you might not see immediately, but are still very helpful and useful. So the first one here is called ImageNet. As you can see, it's a very large data set with more than 14 million hand annotated images. So as you can imagine, that was a lot of labor that went into that. And then across those 14 million images, there are more than 21,000 categories. But something notable about these categories is that there is a hierarchy to them. So you can have, we see sort of 2 examples here where you have sort of a cascading set of categories that are, like I said, they're hierarchical. So this 21,000 doesn't just mean that any one of these pictures falls into only one category, but it could fall into the lowest level one, most specific of, say, husky, which is a working dog, which is type of dog, type of canine, carnivore, placental, mammal. So, it can be an interesting way to develop sort of a hierarchical structure to maybe look if you're trying to develop a method that would be able to have some generalization to it and capture this some sort of hierarchy to it. And so if you want to investigate any of these, I have some links on the bottom right of any bottom right of any of these slides if you want to investigate them in more detail. Another one that we have here is Google Open Images. So this one doesn't have quite as many. The other one had 14 million. This one has 9 million images, still quite a lot. But the additional feature that we'll see in the Google Open Images data set here is, in addition to sort of having labels for the overall pictures, it also has boxes that give you like sub elements or sub features of the images. So this is useful for different types of tasks that you might encounter later, and I'll talk about different type of image tasks right after this section. But this type of data can be very useful for other data types where maybe you're not just trying to summarize an entire image, but are trying to extract individual elements from it. And then the last one that I'll talk about here is called COCO, Common Objects in Context. And this is one where it takes the idea of the previous section or the previous example image, data set, and it then takes it one step further, where instead of just adding the boxes, it adds what's called image segmentation, which I'll talk in a bit more detail, where you can see that the individual objects themselves are being have like a mask associated with them, which gives you a full outline of just those related images, so that you can separate that from the rest of it there. So this one, of course, is a little bit smaller. It's more data intensive to do each of these, and it's just generally a smaller data set, but gives you like a whole bunch of different objects that can be identified, and you can draw the segmentation and the sort of border between that, between a lot of these objects and the rest of the image. So now we'll go into what some of the different problem types are that you might encounter when working with image data sets. Now, this is not an exhaustive list by any means, but these are some broad categories. If you encounter these, that hopefully you can understand what they're trying to say here. So we start off, the most obvious and sort of straightforward one is, once again, this image classification. So let's say you're just, have this plate in front of you, and it would be identifying that maybe you say food or dinner, because this looks like a typical meal that you might have for dinner. However, another step there, another level of granularity, would be object detection. So now it's not just saying, tell me this is food or tell me this is dinner, but pick out the individual parts of this image and label what each of them is. So that's a more complicated task, and it requires sort of a subsection of that. Next would be, as I referenced earlier, this idea of image segmentation, where you have some main objects that you need to identify, and then importantly, you have to find the edges of that object and separate it from other objects, separate it from the foreground or the background. So in that case, your output would be some kind of, something in the same pixel space, but then drawing what the edge is here. So the edges on this would be in yellow, the object itself would be the purple pixels, and then the background or the unrelated parts would be this bluish color. Next up, we have anomaly detection. So this is sort of building on the idea of pattern recognition, but then really looking for anomalies to patterns across a large data set. So for example, if you're looking at the images related to the one shown on the right here, where it's just saying what's a standard piece of fabric that has a zipper in the middle, what would it look like? Anomaly detection is saying we have this damage in the middle or this damage on the outside here, which would be anomalous in this data set. So that would be anomaly detection for this. I will say anomaly detection is something that is definitely getting increased usage in various fields. In particular, I know that there is some use of like AI assisted anomaly detection in medical imaging. Now, you can argue or question, to what extent that should be used in things that require that degree of expertise. But there has been some application to that extent, and for that purpose, in whether it's for tumor detection or for other forms of medical imaging, usually to assist either the lab tech or the physician or the doctor of whatever kind, to maybe flag something as potentially worth taking a closer look at. Another aspect to image data, and this connects into what I was referring to earlier with how data, or how labor intensive it is to collect an extensive image data set, is that you really need, there are a lot of parts of learning in image data that don't that can translate across a lot of different aspects. So if you were looking at, say, my hand, and I were holding it up like this, and then I were to, say, move it closer to the camera, you should still be able to identify that it's a hand. Or if I rotate it around, or if I turn the lights down or up, then ideally we know, our visual cortex, we can identify that that's still the same kind of object. So it's important that, and it can be useful when sort of building our data set, to introduce some augmentations to our data, so that we introduce some of these ideas or some of these sort of changes, so that the model can still pick up and associate that label across these changes. We have this invariance. We want rotational invariance, sort of location invariance as well. So some of the augmentations that we can introduce are pretty much the things I outlined just now with my hand example, but we can do rotation. We can sort of zoom or crop our image so that it's only focusing on a small portion. It should still identify these as, say, flowers. We can flip the image so that it's reversed. We can change the saturation so that you have maybe bolder colors, or we can say increase the brightness. So in all of these cases, the label associated with this image should be the same. And so by introducing these changes, it would force any network that's learning from this to adjust and be able to have some generalizability across all of these variations of this image to still give us the same potential output. Another thing that is useful about this is it allows us to increase our data volume, gives us things that our network technically hasn't seen yet, but should be able to decipher without introducing a significant amount of additional labor, which is, like I said, the limiting factor in a lot of these data sets. So this is something that you can automate to introduce these sort of random augmentations. So I've been talking about how are we doing all these tasks, how are we going to be learning from this image data. Now let's talk about what the networks are that are actually doing, that are actually learning these things. So as you may imagine from the title of this entire section in this seminar is that the type of network we'll be using is called convolutional neural networks, and the underlying function behind and mechanism behind these networks is what we call the convolution. And so what is operating on those is what we call convolutional filters or convolutional kernels, which work as these sliding functions or frames, which operate on subsets or small parts of an image. And then it's applying that same sort of matrix multiplication at each individual spot. And then when you perform matrix multiplication, you're taking I guess it's not exactly the same, but it's effectively you're taking a matrix and then you're doing a pointwise multiplication and then summing all of those together. And then you're summarizing what your total sum is there in sort of a smaller dimensional representation, which we'd call a feature, so a convolved feature. So what I'm showing here is we have our convolutional kernel on the top right here, which is fixed. And it is just for this particular example. And then, as it slides across all of them, we get, since it's just zeros and ones, it's effectively detecting, do we have a location in the positions represented, the corners or the middle here. And so we're effectively getting a count there. Now, when we're using convolutional layers in a convolutional neural network, we might start with something, or we might encounter a kernel that looks something like this. But importantly, when we're training, these are the parameters that we're learning. So we aren't just going to have these fixed kernels that are operating the same way every time, but instead they're going to be updated in order to be encouraged to sort of give us what the most informative features in the image are going to be. When we perform this when we construct this in a convolutional neural network, this isn't just happening one kernel at a time, but it's many kernels and many filters operating in parallel at each layer or at each stage of the convolutional neural network. So what that allows them to do is simultaneously they get to focus on different things. So you can imagine that if, for example, I had this kernel, instead of the ones being on the corners here, if all I had was the ones straight down the middle in the column, just in the middle column, then as that slides across, the value would be greatest there when you have just, say, a vertical line. So then what you could say is that kernel is looking for the single local feature of a vertical line in that space. And of course, it's possible that would be learned. Similarly, you could have ones that are looking for diagonals. You could have ones that are looking for any combination. And these kernels, even though in these examples we're just showing zeros and ones, they by any means can take on any real value here. in order to sort of encourage or discourage different values and pick up on different features. Another thing that's worth noting about this is because this is sliding but applying the same function across all parts of the image, this allows us to recapture some of those properties that I was mentioning earlier about, say, having locational invariance. So it doesn't matter if my hand is, in the top left of the screen or the bottom right of the screen. It should still be identified as the same thing. It's still a hand. Because we're using this filter that's sort of moving across and applying that same function at each point there, it is not relying so heavily on the exact location of the hand and is actually it is preserving that level of invariance there. So that's just a very important aspect of the CNN that I wanted to focus on and make sure was clear here. So there's kind of a lot of parts to constructing a convolutional neural network. And so I wanted to outline some of these just to give you an idea of like, there's a lot of sort of levers that can be tweaked here. So it's worth noting, like, you need to note for how many input channels you have for a given layer. If all you have at first in the first layer of your network is a is a color image, then you're going to have 3 input channels, and then you get to decide how many output channels do you want to result from that. So it will typically be some multiple of your input number of channels. So let's say you have only 3. That means that maybe you only apply a 1 kernel or 1 filter to each of these layers, and then maybe you're trying to get a single output. But let's say you're like, well, no, I want to learn, a lot of different sort of geometric relations in each of these different color label or color filters, color channels. So maybe instead I want 9 kernels or 27 kernels, or pick your number that ideally is a multiple of 3, although it doesn't have to be. And then you get that many different representations at the next layer. So that would be your out channel. Kernel size is defining how big this kernel is. Typically, you'd want to represent it typically it will be square. So you'd want it, say, 3 by 3 instead of 3 by 2. Some of that comes down to what I was referring to earlier, where if you have rotation, but you don't have like a square kernel, then you're sort of biting you're potentially hurting yourself and biasing towards it being in a certain orientation. But you can still play with that, and it'll depend on what your needs are. But you can't, you can choose to make it either way there. And then another thing that will tend to come up is stride. So stride is saying, as we move this kernel across, typically the way this is demonstrated is that we move it once, or we get our first one that's in this 3 by 3 box that gives us this 4. Then we move it over just 1, and then that gives us this 3. Then we move it over 1 more, that gives us another 4. So that is saying that at each step, we transition or we slide the kernel over by 1 pixel or by 1 value. Stride is saying, what if we have a stride that's not equal to 1, say we have a 2, instead of moving over just 1 pixel, it's instead going to move over 2 pixels at a time. And that can be, it'll depend on your data needs, but say you have a very high resolution photo, and as we'll see soon, these can become very large networks with a large number of layers and a large number of different kernels. So it can be a bit of a limiting factor if you're trying to retain very large dimensional representations at each layer, because you could have hundreds of them. So it can be computationally challenging to do that. It can also sometimes be desirable to try and have force your network to learn smaller representations, because that can sometimes help with generalizability. The other aspect is this padding. I won't go into too much detail here, but sometimes you want to add maybe 1 or 2 pixels of padding to each dimension of your image, so that it can make it so that there's less of a bias against the pixels that are on the very outside, because they'll be seen a similar or equal number of times to those that are on the inside. They'll just happen to be butting up against a whole bunch of pixels that are all considered 0. So in addition to these convolutional layers, which are performing which are sliding around and having these fixed but learned functions that move across the whole data, across the entire image. There's often an additional layer which takes place after the convolution in order to perform what's called pooling, which is kind of like a summary, you could say, but it's a way to further reduce the dimensionality of that representation, and can often be a way to help with noise, or it's just been shown that it's helpful to have these pooling layers, whether it's max pooling, which is saying give me the largest value in each of these boxes here to give me an output, or average pooling, which would be give me just the average value across all of these. So this is going to be like you have a predefined boxes and then you give me what those are. This isn't exactly the same as like it being a sliding frame like you'd have in convolution. So before I demonstrate what some of these potential, like what some canonical, previously state-of-the-art CNN architectures look like, I want to demonstrate what really is going on here as I keep talking about the representation and the features that are potentially being extracted by these convolutional neural networks, and why we'd want to do so many of these in parallel. So here I have an example of, say, this cat image here, where we have many different kernels. So in this case, we have, I believe this was 32 different kernels applying at the same time. And once they've been trained, once they've been learned, you can see that each one of these kernels obviously is applying on the same image, and it's picking up on that. But each one is sort of picking up and highlighting and being activated, you could say, by different features of this input image. I mean, for example, there's one on this right side here that seems to only light up when it sees the eyes of the cat. And then we go on, pooling kind of helps us to the max pooling here seems to sort of sharpen those features a little bit, and give us maybe it sharpens more so than smooths it out. But that can be helpful. You want a little bit more, I guess, decisiveness sometimes in these outputs. And then we go on, have additional layers that are then operating on the previous, those previous filters. So now we have, even more so this time we've now, it looks like, doubled, or maybe it looks like doubled or tripled. It looks like doubled the number of filters. So now on each of those, we have on average 2 more filters that are operating, which once again have new representations that they're looking at and slight nuances to the things that they're focusing on, which continues to sharpen once again with the max pooling. But each of these filters gets, a little bit smaller than the last one. So each one's sort of focusing on a slightly different aspect. And as we get even later, say now we're actually 2 layers deeper, we get an even more abstract representation with each one, because we're extracting different things from each thing, or from each layer, each representation in the previous layer, such that in our final representation we have, what looks like a very abstract representation, but these might very well correspond to things that seem very concrete in the early layers. So that's effectively what we're getting in those representations. And then the question is, often in these example convolutional neural net architectures, is what do we end up doing with those outputs? So I'm going to go through these quickly just because it's more intended to be an overview. But you can think, I really like this visual because it gives you the ability to sort of understand how this is, how these operations sort of contort the original images. Where say we have these color images, which are sort of look like this big square with not much depth to them. And then we turn them into smaller squares, but now they have a lot more depth. So you can think of this volume as sort of being twisted around and contorted in a way that it allows us to sort of separate out the features along this new dimension, in which are pulled out by these filters in the convolutional layers. And then typically, in order to perform some final function, we're then going to reintroduce these final output layers into some fully connected layer or fully connected network, which is what we covered in the second session of this seminar. to give us some final prediction of, say, what class these images would fall into. Note that for this architecture, which has 5 convolutional layers, 3 pooling layers, and then a good number, 3 of our fully connected layers, has 60 million parameters. So these can get quite large quite fast. And by the way, this is AlexNet, which came out, this was published, I believe, in the early 2010s, I believe 2012. And then another architecture we have here is called VGG16, which came out in 2016. And this one has a similar setup. We'll have some image that has 3 color channels, and then we'll go through this similar process with a combination of convolutional layers and max pooling before being fed into these fully connected layers. Now note, we had 60 million on the last one. Now we have 138 million on this one here. There are other architectures like this GoogleNet architecture, which uses this idea of like an inception module, which I'm really not going to go into too much detail here, but just gives you the sense that like this is a small little module that can be repeated several times over, which are almost like individual layers in themselves. But really, what I want to use these is to emphasize that there are a lot of different ways that these convolutional layers can be sort of packaged together and strung together in order to perform these tasks, and can have a very large number of parameters. But this is something that requires a lot of playing with, unfortunately. But hopefully, once you get into it, like you can start developing some intuition. I usually recommend starting with maybe a published architecture for CNNs, and then adjust it how you feel, because they can be a little bit challenging to work with. So for the second half of this, I'll try and move quickly because I know we're already about half an hour in. But I want to talk about autoencoders and latent spaces. So as I mentioned before, first session, we talked about proper orthogonal decompositions in the form of singular value decomposition, principal component analysis. Another one is called Kerr-Huhnen-Loewe decomposition, which is a similar idea, but using more of like it's more of a stochastic context, so more of a probabilistic instead of deterministic setting. But a major property of a lot of these decompositions is that we'll have in many types of data, a few or a small number of directions or dimensions can capture a majority of the information that's useful for explaining the variance in that data. So many times we can demonstrate this by reconstructing our original data using just a small number, like I'm showing on this right-hand side here. We talked about these types of examples in session 1 as well. So this is a well-known property of a lot of different principal, like PCA, for example. But so when we're working with autoencoders, the idea is to do something similar, but instead of having some fixed sort of algorithm like we have for PCA or SVD in order to do this, the encoding and decoding of that space is something that is learned. So this is going to be a data-driven approach for performing this. So the idea, the structure behind this really is you'll give it we have some input data that we provide to an encoder, which then represents it or projects it down to a lower dimensional latent space. And then the decoder then takes that latent representation to try and then reconstruct that original data. And then our loss is typically evaluated by looking at the distance or the difference between the input data and our reconstruction. So ultimately, we don't need to have some label on this input data. It could be an image. It could be many other things. Because we don't need an input on it and we can still generate some kind of loss, this falls into an unsupervised learning category. And you'll see this is very equivalent or very similar to our various PODs or principal orthogonal decompositions. So let's look at a comparison between what's different between the autoencoder and the POD. So as I mentioned, our encoder is going to be projecting into a lower dimensional latent space. That latent space is something that needs to be defined ahead of time. So that's a hyperparameter of your system, of your network, which is different from a principal orthogonal decomposition to an extent, because while it is constrained by, or the total number of dimensions in your representation for say PCA or SVD is going to be determined by the total size of your input data. What you use for the low dimensional representation is something you can just choose after the decomposition has already taken place in order to perform some kind of reconstruction. Autoencoders instead, when you start the learning process, you have to determine, do I want this to be 10 dimensional, 20 dimensional, 5 dimensional, 100 dimensional? You have to choose ahead of time. That said, if you decide you want to instead look at a higher dimensional or lower dimensional representation, then you can train it again using a new system with a lower dimensional latent space. However, you can't just take. It's not like you can directly transfer, say, a higher dimension, what you learned for a higher dimensional latent space directly to a lower dimensional latent space. You do have to start from scratch. For the autoencoder, the decomposition, so both the encoder and decoder are learned iteratively, and the functions are not necessarily linear. So typically, your SCA or PCA and SVD, those are going to be sort of linear functions that, or they're kind of directly invertible, whereas in autoencoder, each of the individual functions themselves is not linear. They're not necessarily invertible explicitly. And then importantly, the representation in the latent space, unlike the factors of your PCA, so unlike your principal components or unlike your right or left singular vectors in SVD, they are not inherently orthogonal to each other. So there will be some mixing there. There will be some richness to that representation that can complicate things to an extent, but also give some flexibility. So just focusing here on the structure a little bit, as I mentioned before, the purpose of the encoder aspect of this network is to take our input and then represent it in this lower dimensional latent space. Most frequently, autoencoders will start by using, and the easiest will be to just use some fully connected layer, fully connected network as your encoder. However, there's flexibility to that, especially depending on what your input data is. It might make more sense to use a CNN or some convolutional layers or some recurrent layers to some extent. It just, it'll come down to what you want your latent representation to end up having. Similarly, yes, there's a question. Oh, okay. Well, they're missing a little bit. So yeah, this is why I usually have a co-host, so thank you. Okay, so then when we look at the decoders, this is going to be effectively doing the inverse there, because as I said, when we're performing this autoencoder, the idea is to have our input and our output. We're comparing them to each other, and we effectively want the output to match the input. So really, the decoder is trying to learn to an extent the inverse of the encoder, even if it's not taking that exact function and doing the inverse. So it's functionally an inverse. So similarly, it can take on those same features where it can be fully connected, a CNN and RNN, whatever you choose for that to be. And it will be, to an extent, it will be enforced to provide the output that, or output the, an image or a data that is matching your input. So let's dive a little bit more detail then into what this latent space representation is, because that's really storing a lot of information and data here. So the features that pop up or that are represented here in the latent space, as I mentioned before, are not necessarily orthogonal to each other as they would be in the classical data data decompositions that we talked about in session 1. Additionally, they are not ordered like they would be for SVD or PCA. So really, you can have you could have a very even or equal representation across all these different dimensions. Well, I would say that once you start diving into this in more detail, the parallels to the proper orthogonal decomposition probably start to fall apart to some extent, just because the purpose of what they're serving becomes different at this point. But What's very useful about this type of representation in the latent space is that they can be, you can introduce aspects of your network and of your training to encourage certain organizational structures and certain geometries of your latent space. So there are, I'll show this a little bit on a later slide, but it can be, you can sort of encourage your network to have a separation in the latent space of like semantically relevant features. So for example, if you have an image where you're trying to find out how do I represent this, you might assign some value or certain dimensions of your latent space might correspond to some property of the hat and maybe what the rotation of the say of the person's, person's face or person's shoulder is, the color of the hair, eyes, background, etc. So it can fall into a lot of these different categories, but it's something that you can encourage over the course of training and how you construct your data set. So there's some interesting features that you can extract within this latent space. So something that can pop up there, especially because really the purpose of this latent space is to find that the encoder is trying to do is find some representation in this lower dimensional space that allows the decoder to successfully sort of separate it out to understand it and faithfully reconstruct it. So that latent space needs to contain a lot of information and find a way to tell a story, communicate all the necessary features of the full dimensional space in this lower dimensional space, such that it can be inherently learned by the decoder, because it's not going to be told ahead of time how it is to do that. So an example that I'll show here is actually from a paper that I published a couple years ago, where say I was looking at the properties of some recurrent neural networks, and I won't go into too much detail here, but effectively I was able to, I was looking at the error of different networks depending on what their on what certain hyperparameters were, and I wanted to try and understand. I used an autoencoder effectively to try and separate out these networks that had low error from those that had high error, based solely on a particular property of the dynamics of that network. Like, I'm not going to go into too much detail here, but what's helpful is that just in the representation of the latent space here, the networks that corresponded to this low error, this green, were separated out in this bottom right corner of the this two-dimensional representation of the latent space, whereas the ones that had higher error were separated out into more in the upper left portion of this space. So this can show that even just looking in this space here, training an autoencoder can give you a lot of interesting value. And then of course you can sort of play around with what's going on in that latent space itself, which takes us to this idea of latent space manipulations. So this paper that I have shown on the bottom right corner here is it took an autoencoder and used manipulations within the latent space itself to try and encourage and generate images that had that sort of covered a spectrum of particular properties of that image. And this was the one that used that idea of separating out the latent space in certain like semantic directions. So for each of these images, they identify certain features that they're then able to sort of twist the levers on by introducing small changes in the latent space to give a different output. So for example, they can say, me, every time that I have a chance in any of these, I'll always use a cat example. So let's look at the cat row here. One of the features that it looks at is the posture, where it can go prone to upright. So if it goes all the way in the prone direction, then the output image is the one on the left here, whereas more upright would be on the right here. Then it can have one where it zooms out versus zooms in, or it can change the hair color from white to black. But this is all based on this same initial image with no, say, changes or manipulations in the latent space. It would give us this. But then in this representation, we're able to go and make some tweaks there such that the decoder gives us a different output here. So that gives us sort of an interesting, hopefully an interesting visualization, an idea of what we can do in the latent space, and use the fact that we have this encoder and decoder to give us a lot more flexibility in understanding maybe what artificial changes in what our potential input or our potential representation could be, how that could change what the output might be in this construction. And then I'll briefly go over I call a variation on this, but what we call variational autoencoders, which are a more probabilistic or statistical approach to this latent space representation. So really, instead of taking one individual, say, image or one individual piece of data and giving it a deterministic representation. Sorry, I'm gonna ask everyone mute. So we have instead of a deterministic representation in this latent space, which then gets decoded to try and reconstruct the original input data. Instead, it is representing it as a distribution where it might have different features that it's learning to represent, that the encoder is teaching it to represent. But then the decoder is, instead of taking that and doing a direct mapping, it is then using that latent representation as a distribution from which it will then be sampling in order to create a reconstruction. And so since we're looking at comparing, a distribution, and we're looking at these things that are more of a probabilistic and statistical representation of our data, in addition to maybe wanting to use a more standard, say, MSE reconstruction loss, we also want to look at how those distributions are different from each other, which is why we'd introduce this KL divergence. So I promise, as usual, I always say I'm not going to go too math heavy in these slides. I'm breaking my one promise of saying anytime I put an equation, I'm going to go through all the individual little details, because I don't think anyone wants that right now, and I don't think it's going to be super helpful, except for just explaining how KL divergence is going to be giving us a way to measure the difference between two distributions in sort of a distribution space. So really, we're looking at, what is our distribution of, or how do we look at our loss based on what we got for our decoder distribution. Excuse me. Our decoder distribution P, given what our encoder distribution Q is. A lot of things going on here, and I don't want to focus on this in too much detail, but just to understand that we would introduce this additional term for the variational autoencoder. This gives us a lot of interesting flexibility, and variational autoencoders are actually very powerful tools that get used for a lot of interesting applications, which I'll get to on the very final slide. I also just want to point out what this KL divergence is doing for us, and why it's important for trying to learn these distributions and learning for variational autoencoders. Given that, if you're just trying to sample, and you'd be very biased to take just like, say, a single sample and say this is the average right here, and maybe give it a very narrow distribution that you're representing it by in this latent space. Because if you do that, then the odds of the reconstruction being very similar to that become very high. But that's not necessarily, that's only helpful for that one example, for that one piece of data. And as we've talked about in many cases before, when we're learning using neural networks or machine learning in general, just getting one sample right is not the solution. We have to find, how do we get a very accurate representation using this data, such that when we see new data, it will also have the flexibility to do that as well. So the KL divergence, because it acting as this regularizing force that's encouraging a more smooth latent space here with a wider standard deviation or a wider distribution here, so a larger standard deviation closer to zero mean. That means that in order to sort of overcome that regularization, it would need to be like such a perfect fit for not only this data, but many other data which are much like it. In which case, it would be accurate that the distribution would be very narrow because there's so little variation across the different sets. In which case, it was very helpful. Like, it's still good that we did this because it opens up the opportunity for more generalization across that. And then just as the final slide here, I just want to point out that there are a lot of ways that these variational autoencoders can be enhanced or changed a little bit in order to encourage different properties of the latent space and of how we sort of sample this distribution. So I just have 3 different papers here that perform different functions. I realize this has been already a pretty long session, and I want to give people a chance to ask questions before we go overtime. So if you want me to go into any of the details here on these different VAEs, I'm happy to do so, but that will conclude what I was going to talk about today, and I'll just open it up for questions. Yes, we have a question in the room.
Yeah, for the first part with the CNN for the image classification.
Yes.
We have a slide about different like step of classification, but like can identify what is the image, can segment where is the thing on your image.
Mm-hmm.
Like for the segmentation part.
Yes.
Is it also can this also be done with the same kind of CNN network, or that's just for classify that like that's an apple in this image and not where the apple is?
So the same structure would be used. The differences that you would see are what your output is and what your labels are. So and like the loss function that you're using, because you'd penalize it differently, because effectively you would, if it's just straight classification, then all you're doing is you're saying, tell me, all I care about is, was this image correctly identified as this class versus that class? When you're looking at, say, object detection here, you're saying you have to give me location and the classification. So you do a hybrid sort of loss function there, where you're looking for 2 different things. Image segmentation is also going to be similar, where you're saying maybe you're not concerned about identifying the exact object anymore. Maybe you are, but let's say you just care about the segmentation. Then what you're going to be comparing is, here's what the actual mask should be. Here's where the lines of here's where the borders of that mask should be. You could say, was this correct? You might say, what's the distance? How far off are you from the nearest thing that was actually supposed to be the mask? You'd have different ways that you'd construct the loss function there. But the parts behind it, the convolutional layers, that kind of thing, those parts could be the same. Those still have a lot of flexibility. You might have different ways that you do the final layers, like the fully connected layers might have a different thing that you're trying to say or trying to sort of represent it as, especially like if you're looking at the image segmentation. That one, you need to make sure that the output is back in the original image space so it can match up with your labels and your mask. You can't have it where you're just like, you wouldn't want it represented as just a like a vector, unless those vectors were, you could say that you could do it as a vector, which is representative of space, but ultimately that's still going back into image space. So yeah, that's a great question. Thank you.
Okay.
Yes, follow up.
Next question. If for example, if you want to track something like kind of in a video.
Yes.
Kind of more related to the previous session for like sequential type of thing, maybe, but
so it could be
with the RNN.
There would be generally typically you'd have some kind of combination of the 2. It would kind of depend on what exactly you'd want to do, but yeah, when using videos, you'll have some recurrent aspect of it, and typically you'd use convolutional layers as well. So there'd be a lot. But typically what you'd want to do is, I don't even remember what order you typically want those in. I think generally you'd probably want to do convolutional layers first and then a recurrent layer. So your convolutional layer will give you give you an output for the first frame, and then a recurrent layer is learning something from that, and then second frame. So that becomes the output of the convolutional layer becomes the input of your recurrent layer, is how I would typically, that's how I would expect that to be. And then the output of the recurrent layer would perhaps give some information, like you might, maybe you would find or want to find a way to like feed that into some seed to inform something about your convolutional layer as well. But typically you might be able, I think you should be able to do those in parallel, like hopefully without too much interacting. But I'm not too familiar with video processing too much for that kind of thing. But video tracking is pretty well established. You've probably seen it quite a bit where you have the boxes where it's like tracking different people moving, and so that's well used, and I know that it would use a combination of both of them. So thank you for bringing that up. Yeah, I chose not to dive into that too much here because already we have a lot of content before getting into any of the time dependent aspects. Any other questions? Oh, another question? Go for it. Yes, please. Please, thank you. Yep.
If I understood well, like the goal of using that kind of tool is to get the information like hidden in the latent space more than the reconstruct output of the decoder, right?
Yes.
Like you don't really care like about well, you care, it needs to match, but it needs to match to, and what you want is the latent space to
Yes.
do more information.
Yes. So the question here is the purpose of the auto is a clarification that the purpose of the autoencoder and what we really gain from it is the latent representation. It's not necessarily just the reconstruction. And yes, so I mean, there are some times where I've heard of autoencoders being used in I believe in like a sequential reconstruction task of some kind, because there's a base assumption that your output at the next step is going to be very similar to the previous step. So then you like do a yeah, I don't know. I can't speak to that exactly. I don't remember exactly how it works, but I could look into that in more detail and try and find that paper for you. But yes, like, I mean, similar to when we perform our SVD or PCA, right? Just doing the full dimensional reconstruction of PCA is literally just the original image. Like that's not interesting, right? What's interesting about PCA is what are the first two components, or what is the low dimensional representation? What are the first 5 components tell us, and how much can we get from it? So that's really what the latent space is, recreating that, but with more computational flexibility and in a data-driven way.
And how do you choose the number, the dimension in your data?
It's however many you want. Typically, you'd want to do it where there could be a point where if you pick too few, you can't reconstruct, right? Like that's where seeing a reconstruction and looking at the output of your decoder can help, because you need some limiting principle on how small you get, because otherwise, then you have a 2-dimensional latent space of your original 500-dimensional system. Like, okay, cool, but you can't actually construct anything out of that, so it's worthless. So you'd have a high loss for that anyways. If you're able to get an autoencoder set up such that the loss converges and it's able to successfully reconstruct on your entire data set, then that's great. And usually you'll either, like I said, you'll look for maybe the lowest dimensional space that can do that, or you might introduce other aspects of like other regularizers or other constraints on your latent space to try and tease out certain features. So you could maybe introduce an additional loss, for example, so that you encourage the latent space to do something in particular. So that's where there's a lot of flexibility, because you get to decide what structure you want that latent space to have, as long as it satisfies the basic overall condition that it encodes and decodes, successfully. But all of that, that's the boring part of the autoencoders. The fun part is like figuring out how you're gonna deal with that representation in the latent space.